congratulations, you are finished with the electric field for now. We've done the basics, we made the field, we thought about the forces, we thought about the potential, we used Gauss's law. That's the good news. We're done with the electric field for now. The bad news is that means we have to do the magnetic field. The magnetic field. It is so confusing. It's just bad. There's just nothing good about the magnetic field. It's mysterious. It's got sort of a mystique about it, but teaching it and learning it, especially halfway through the class, it's not good. So what I'm going to try to do to help is, I think the problem is how we start the magnetic field usually. We sort of go with this historical introduction. Here's a bar magnet and here's field lines, and don't worry about where they come from. So I'm going to do just one board on the big picture, comparing the electric field, where it came from, what it does, to the magnetic field, where it came from, what it does. And by understanding why you get so confused, it might make you less confused as we go. Okay, so that sounds like a brilliant way to start the magnetic field. So let me just go with this. Like E, the magnetic field, which we call B, and I don't care what happens, I don't even want to answer the question. I don't know why it's B. Okay, so there you go. Don't even ask me why it's B. Is defined by force on charge. So they at least have that in common. They both involve charge. They both involve force. So let's think back a little bit to our electric field. Very straightforward idea. This charge creates an electric field and uses that electric field to create a force on this charge. And really just the electric field was something we made up as a way to describe the force. So Q1 creates E and then pushes Q2. And that's pretty much it. Magnetic field, here's how it's different. For the magnetic field, at this level, the only difference is it's moving. A moving charge creates a magnetic field, and this is just a schematic, that's not necessarily the direction that the magnetic field would be. It creates some magnetic field that pushes a moving charge. Things have to be moving. Okay, so Q1, so a moving Q1 creates B, and it pushes a moving Q2. The charges have to move. If these charges are not moving, you just have the electric field and the electrostatic force. If they're moving, you might also have a magnetic field and a magnetic force, in addition to the electric field and the electric force. So when you let the particles move, the forces change. And the new forces that show up, we describe with a new field called the B field. So the two are very much related. We just don't really introduce it that way. It's also, if you think about it, it's a little bit mind-blowing. Here, whose mind do you think it blew? It blew Einstein's mind. So you've heard of Einstein and relativity. So he wrote his famous paper in 1905 about special relativity, and if you try to study that in your freshman physics book, there will invariably be a problem or a thought process about a train and somebody on a train holding a stick or throwing a ball and all this stuff. That's not how Einstein was thinking when he wrote his first paper on special relativity. His first paper on special relativity was called The Electrodynamics of Moving Bodies, his 1905 paper. This is what bothered him. If here is a charge, say, let's not even have this diagram here. I wasn't there, this is maybe exactly what bothered him, but this is kind of the idea. If Q1 is sitting there, and I'm standing here, and I look at it, I see an electric field. And now if I start moving, now Q1 is moving relative to me. So suddenly I see a magnetic field. And then I stop, oh no, it's just an electric field. Then I start moving again, and I see a magnetic field. So the fields that you see depend on your inertial reference frame, as they say. It depends on the relative motion between you and the charge. that's strange. And if you throw in light, which was known to be an electromagnetic wave, things become even more problematic. So it was really these kinds of ideas, why you have E and B is only there when things are moving. That's one of the things that really pushed Einstein to think about relativity. So this is, deep, heavy stuff. I'm not telling you this is trivial. But I think if you can think about it a little bit this way and realize this is what's happening, it might help you see where we're headed when we do the historical introduction. Another difficulty is in math. So what is this force? This push is a force. So what is it? Well, I'll write it real quick just to show you what's coming here, is that the force, I'll just give myself a little room here. The force on a charge, we know the electric part is QE. Use the big Q. Is the charge times the electric field. That's how we defined it. And we just have to multiply a scalar times a vector to get a vector force. But then the magnetic part is also the charge, Q, but then we have to involve the velocity and the B field, and those are both vectors. So we have to multiply out two vectors to get a vector. So you can't do that by how are you going to multiply them? So dot product doesn't work because that gives you a scalar. So when you multiply two vectors and you want to get a vector, you use a cross product. QV cross B. And we'll talk about what that is if you don't know what the cross product is. But what it results in is just conceptual difficulty. The electric field, if the electric field is facing that way, it pushes that way. If the electric field's up, it pushes up. This cross product makes the B field push things sideways. So the B field is this way, the velocity is that way, it pushes this way. So you really have to think in all three dimensions to do the B field problems. And then it does worse things. It causes things to go in circles. Everything's all loopy with a magnetic field. Okay? So prepare for all of these problems and be thinking about them in the back of your mind as we start the more normal introduction to the magnetic field. The way we normally introduce magnetic fields is with one of these, is with a bar magnet. So usually you draw it as a rectangle, although it's usually a cylinder in 3 dimensions. And we have put an N up here and an S down there. That's the North Pole and the South Pole. The fields coming out of a bar magnet kind of look like this, with the field lines emanating from the north and curving around to the south. And then this one kind of does like that also. And they're going in all 3 dimensions, some kind of like that. And I'm not going to give you the equation that makes that field. Like I said, this is not as straightforward as the electric field, where we just have the equation, Coulomb's law, giving us a field around a point charge. This is more complicated because it has to do with what's happening inside this material, which we're going to slowly figure out. Bar magnets were of great interest in ancient times because the natural materials that did this would always point north if you float one of these on water or if you hung it from a wire. And the reason is they feel a force that makes them align with the Earth's magnetic field. Okay, so if I draw the Earth here, all right, and if I draw some of the important structures of the Earth, like this, there, that's the Earth. This is the North Pole, and this is the South Pole. So Santa Claus lives here and the penguins live down here, okay? Now, we know then that the Earth has its own magnetic field where the field points basically this way. It points from south to north. Okay? So this is why if you take a bar magnet like this or any magnet with a north and south pole, it'll align to where it points north. The North Pole points north. So that's why we call this north and south, right? That's the historical reason that it got that name. If you look at this, you might quickly see something a little bit confusing. If the field is going that way outside the Earth, it seems like the names of north and south are wrong, right? Because the field lines are supposed to go on the outside of the magnet, they're supposed to go from the North Pole to the South Pole. And here I have them going from south to north. And then you may have heard of magnetic north. Now, magnetic north just means the field lines are actually a little bit crooked. Magnetic north is like over here somewhere. But that doesn't solve the problem, right? It's still, they're going the wrong way. And the reality is the Earth is upside down. Magnetically speaking, freshman physics speaking, the Earth's, if we consider this same geometry of the Earth, the North Pole of the magnet inside the Earth is at the South Pole, is at the bottom. The magnet's upside down, such that when it makes field lines outside, they point north. Okay? So when you think about this bar magnet aligning with the Earth's field, it really is aligning with a magnet inside the Earth. And then you also see that magnets like to anti-align. They like to get the north with the south and the south with the north. If I were to align this little magnet with this bar magnet I drew and this were north, it would want to do this because it wants to align with this magnet's external field. And if this one, it's aligned with this magnet's external field. See, this one is going like that. Okay, so that's how two magnets interact. So, as you can see, there's no equations here. So next, let's see if we can chop this thing up and get down to something where we could write an equation. So I've told you about the magnetic field lines around magnets and around the Earth. Many things have magnets in them and have magnetic field lines. One is this. You may have seen these little magnetic bracelets before. And it's a little silver band with gold balls. But if you look right on the inside edge of the balls here, there's two little magnets embedded inside. So let's think about what those magnets are doing. So it looks something like here's a ball, and the thing goes around, and here's another ball. It's very pretty. And the magnets are more or less here and here. And if they're smart, they put them like that, north-south, south-north. Therefore, you have magnetic field lines would kind of go like this. Okay? Created by this magnet. A little field extends from one ball to the other. Now, when you put this on your arm, like this, they're against your arm, like that. So it's creating the magnetic field inside your arm. So here's your arm in cross-section. There's your bones, radius in your ulna, I think, a bunch of blood vessels. And this magnetic field inside your body is doing absolutely nothing. Okay? They sell this as a remedy to treat pain and all kinds of conditions. It does nothing. This little magnetic field in your arm, in your body, has never been proven scientifically to do anything. And the people that sell this should be ashamed of themselves that they sell this on the public, the gullible public, to think that these magnetic fields are going to do anything. If it makes you feel better through some placebo effect, that's wonderful. Let it make you feel better because it's pretty. It makes you feel pretty to wear it. But don't believe that the magnetic field is actually doing anything to your arm. Let's compare this bar magnet to electrostatics, because we're really good at electrostatics. Let's think about something called an electric dipole. So if we have a charge here, a positive charge, and we connect it to some negative charge with a little stick, an imaginary stick that keeps them separated, that's a dipole. It has two poles, a positive pole and a negative pole. And let's imagine this one is fixed. Okay. Now let's have another dipole here. Let's let this one have its positive charge like that, and its negative charge like that, and let's put it on a pivot. Okay. So it can't translate, but it can spin, it can rotate. So what would this thing do? Let's see. So it would feel a repulsive force here, do those two positive charges. It'd feel an attractive force here. So the net force would be down. Together, those would want to push the positive charge down. And then the negative force, the negative charge would feel a force that way, and it'd feel an attractive force that way. The net force would be up. Okay? So the negative charge would feel a force up. And it's on a pivot point, it's feeling a torque. So it can turn around this point, it's fixed there, and rotate. So what it's going to do in the end is it's going to align negative here, positive there on its little pivot point. That's what electric dipoles like to do. This is the lowest energy state, is what you'd say. So what we just saw was the same thing for magnetic dipoles. Okay, magnetic dipoles, if we have north here and south there, we just said they like to align like this. We have south here and north here. So it's basically the same thing. Now, it would seem then, if in electrostatics we can separate these and have different charges, that in magnetic fields, if we wanted to figure out the equations that are going to lead to this, we should be able to just cut these in half and then have north charges and south charges. That'd be what's called a magnetic monopole. If all the magnetic effects are contained just in one pole, and this is a free particle, then you have essentially a magnetic charge. Problem is, no one's ever found one. Some physical theories predict they should exist, but they never seem to show up. with this bar magnet, you'd say, well, we just got one, we cut it in half. But that's not what happens. If you take a bar magnet and you cut it in half, north here, south here. Cut it in half, and you get north there, south there. And you cut it in half again, you make a little teeny one, you get north here and south there. And you cut it in half again, you get one like this big, north, south. You can never separate the north and the south. They're inherently mixed together. So when we start to tie this to electric fields, maybe we'll be able to see the reason why. So we've seen that electricity and magnetism started as separate things. Electricity was all about rubbing cats and those things, and magnetism was all lodestones and compasses. But many researchers and scientists in the early 19th century thought they were probably related. It seemed like they seemed similar. So one physicist that was investigating this was Hans Christian Ørsted, but he did not did not discover the link in his research lab. He actually discovered it while he was teaching class. So he was doing a lecture demonstration, and he had a wire with a large current going through it, and he got a magnet kind of close, and he saw the magnet needle twitch. And that was the first discovery of the direct link between electricity and magnetism. So we're going to reproduce that for you here. Here's a large wire that can pass a large current, and it's hooked up to this switch and this power supply, so we can pass about 10 amps through the wire. And here we have 3 compasses with their magnetic pole pointing to the north. That's north in this building. So right now they're aligning with the Earth's magnetic field, because that's what a compass likes to do. But let's see, when we turn on the power supply and I throw the switch this way, now current's flowing one way, and now they've all aligned like that, because the current created a larger magnetic field than the Earth. So now they're aligning with that magnetic field. If I throw the switch the other way, they go the opposite direction, because now the current had created a magnetic field the other way. So we can go this way, this way, this way, this way, or we can let them go with the Earth, and then they get really confused and upset. And I'm passing a little bit too much current through my electrode over here. So I think that's the end of this demonstration. Let me turn this off. And now let's think about how we could draw the fields around this wire. Ørsted showed us that a current can make a magnetic field. So what we're going to do is look at a few geometries of magnetic fields created by currents, just to get a feel for what they look like. We're not doing the equations yet. That's for later. Right now, let's just see what happens. So first, let's look at a long, straight wire. And when I'm talking about wires in this section, it's implied that they have a current flowing through them. I'm not going to write out carrying a current every time. So a wire, and of course, it's carrying a current, because that's the whole point. Okay? So here is the wire. It's got a current flowing through it like that. So if you have a long straight wire with a current, then the magnetic field just makes loops around the wire. Little cylindrical field forms like this. And it goes from behind the wire up to in front of the wire down when the current flows in that direction. One more. Ooh, okay. Yeah, and that like that. So you can see why it caused the the compass's needle to turn. If we had the compass here and say north off like that, the needle is pointing like that for the Earth's magnetic field. As soon as we turned on the current, the needle moved because it was being pushed by this magnetic field. We created a field much larger than the Earth's magnetic field. And that's how it was first discovered by Ørsted. But the visualization, or the way the field would look, if you were to look at it, is it's cylindrical lines, or it's lines going around a cylinder around the wire. Let's look at another one. Let's look at a wire loop. Okay, so just a little circle of wire, of course, with current going around it. So let's see if we draw it kind of like this. So there's the loop, the current is going around like that. This is the back and this is the front, kind of looking down on it. This will make a magnetic field that goes up like that. It goes through the loop. And when you get off to the side, it kind of starts to curve out like that a little bit. And it might kind of go like that. And it might kind of come, oops, it might kind of come like that. Okay? So it just makes a field that kind of goes through the loop, and then it actually comes back around to itself. Okay? So that's the current. These are the field. And actually it matches the wire case. if you look at it and you say, well, right around the wire, it needs to circulate around the wire, and it does. See, this is going around this wire carrying current. This one is going around this wire carrying current. But in the middle of the loop, the part you care about, it's a way to make kind of a uniform field, a field all pointing in one direction. Later, if we stack up a bunch of loops, then it makes a really uniform field. It makes a solenoid. Okay. We can also then, now that we sort of understand that, we can think about a magnetic material. So remember, we had the bar magnet, and it had a north and south pole, and it made a field that kind of went from north to south. But now we can actually understand what's happening. Why is the bar magnet doing that? It's because it's filled with microscopic current loops. The little atoms inside the magnet make little current loops going around. And in most materials, all these little current loops, due to the atomic orbitals and the electron spins, they all kind of just cancel out. But in some materials, they don't cancel out. They line up, and they give you a big magnetic field. Now, to make it match this, you've got to see that inside the magnet, this is confusing. When you think of a bar magnet, the field goes from north to south. But inside that bar magnet, there's a big field adding up, going from south to north. Because just like this current loop, if the current's going around like that, the field comes from the bottom up and it goes around. So you can see a bar magnet, or a magnetic material, a magnetized material, is just millions of teeny, teeny current loops adding up. And the magnetic field we experience is the outside the loop magnetic field. Okay? So a current loop is actually very fundamental. So when we think about magnetism, a current loop is so fundamental, it gets its own special name. It's called a magnetic dipole moment. So let's think about that for a minute. First of all, why is a loop fundamental? You think if something's fundamental, it's a line of charge. When we think of what is sort of the fundamental thing that gives you magnetism, you want like an isolated little small thing. So this can't be an isolated thing. This is an infinite wire. The current had to start somewhere, the current has to go somewhere. There's no way to make this a thing. The only way to make it a thing is to make a loop. So here's something little that we can hold in our hand. Right? You can't hold an infinite wire in your hand. But when you take a current that has to flow and you make it go in a loop, now that's sort of a thing. Okay? And now you can start to see when it flows, when current flows through this loop, that sort of one side of the loop is the north pole and the other side of the loop is the south pole. And that's why when they line up, we call them the north and the south pole. That's why it's a dipole moment. A monopole would be a charge. In electrostatics and electricity, we have charges that generate the field. In magnetism, it's always these loops. And this is why you can't ever separate them. This is why you always have to have a north pole and a south pole, because there's no way to cut this in half and just get the top or the bottom. There's always a top, and there's always a bottom. Even if you cut this wire in half, you'd have two wires, two loops, just like before when we talked about cutting the magnet in half. Okay. So mathematically, the magnetic dipole moment has a name. It's mu equals I times A. So the magnetic dipole moment is a vector called mu, and it's simply equal to the current flowing around the loop times the area of the loop. And it's that area vector we're familiar with where you pick a direction, or where there's a direction for the area vector that's normal to the loop. Okay? So mu equals I times A. So usually we don't draw it quite so fancy. We could just draw a loop like this with the direction going like that, the current going like that, and mu sticks up like that, just like the area vector would. So we're going to use mu when we think about how things interact with magnetic fields. But it is the fundamental magnetic source, is a magnetic dipole moment.